Thank you, Gano, for that kind introduction. So, the title of my talk is Going from a 5G Vision to Real Implementation. As we all realize, that's a very broad scope. So my intention with this presentation is actually just to highlight a few trade-offs that you might find when you put these systems together, primarily from an antenna point of view, and how that relates to the transceiver design down the road. So if we start with just what's driving the 5G business, as Gernot already said, I mean, 5G is on the horizon. We have already started to deploy these kind of systems, but it's primarily driven from a business use case perspective, where we already 2 years ago saw the first fixed wireless access networks being shaped in the US, and now we are moving into the mobile broadband domain, and on the horizon we have the massive machine type communication that will show up, both when it comes to, I mean, the critical time or critical kind of communication where latency parameters and such will become paramount, but you also have the massive kind where you need to scale up the IoT connectivity to a whole new dimension compared to what we have today. So my outline for this talk will be just first to address the topic, what does this all mean to the radio? I mean, we are radio designers here and look into the radio perspective, so what does it mean for us? Then we will move into the antenna array systems, and we'll talk about some trade-offs, some challenges, and then finally we will look into a simple model how to try to digest how different antenna array systems will play when it comes to the power consumption of the system. So that is the outline, and the first part then is about the 5G radio. And from a radio perspective, you could view this from 3 different angles, as I see it. The first one is, of course, we will introduce new frequency bands. We need to find more spectrum in order to meet the demands for data rates here. That means that we will have to move up to millimeter waves. You're all aware of that. We'll find larger chunks of bandwidth, and that will also bring us to a situation where, from a deployment perspective, you need to combine bands in a totally new way than we have seen in the past. And this is due to that there will not be a specific frequency band suiting all the different requirements we will have. So band aggregation will be an important part of this puzzle. So just a short example as an introduction. If we go up to millimeter waves and we make an ordinary deployment, let's say we would just bring everything we have, put it on millimeter waves, what would happen really? In this example, if we regard a 28 gigahertz carrier with certain parameters of bandwidth, etc., we see that for a given SNR that is required for the link, we can assign an SNR for the RX and the TX. And if you just calculate what this will bring in terms of distance, you realize that for an isotropic system, you will get something close to 15 meters if you just view ordinary power levels that we have in electronics today. The picture on the right-hand side, that's a commercial GaN PA from Qorvo, and everything is sort of off the shelf here. But it will bring us a system that is not very deployable from a cellular perspective. So we have to do something about this. And what we do today is that we move into antenna array systems. We need to bring up the antenna game. And since we would like to, in essence, increase the antenna area, and we are still limited by lambda, we have to bring it up by scaling antenna elements, and that is the array concept. So we're using the classic Friis formulas from the 40s, and we see that if you scale up the antenna element on one side, keep the aperture that is lambda dependent to the square, we see that basically the link loss will be kept the same. On the other hand, if you're able to scale up both the receive and transceive antenna, then you would actually gain. So this is the traditional solution that we all are targeting today for these kind of systems. On the other hand, I mean, this also provides us an opportunity. When you have antenna arrays, you can also direct beams, meaning that you can have spatial multiplexing, spatial isolation, and that will actually provide a gain for the system in the end. We will come back to that part. So if we go back to our millimeter wave example, if we're able to scale up the antenna from being isotropic to having 64 antenna patches, and we also scale up the receiving part, so you're not having just an isotropic antenna on the UE, but maybe on 2x2 antenna array on that side as well. You see, if you plug in these numbers in the equations, we have increased the range to 700 meters by just doing the antenna redesign. If you on top would add power, since you now have 64 elements on the transceiver side, you could in theory add 18 dB more power, and then you would end up at 5 kilometer range. So you see the power of working with the antennas instead of just working on the PA side and try to put up more power. That would be very, very tough. The antenna gain is so important. So this is the background where we are so keen on working with array antennas. If we study an example in practice, this is a ray tracing simulation from Covent Garden in London with an intersight distance of 400 meters. And we compare two systems, one 3.5 gigahertz system and a 26 gigahertz system. And we look into the coverage. And of course, the color coding here is not that, it's not crystal what it means, but dark green indicates roughly a bit rate of above 1 gigabit per second. If it's red, you're down to below 10 megabit per second. And if it's white, there is no coverage at all. And what you can see is that from this simulation, we realize that the 3.5 gigahertz band is very useful for coverage. We all know we have good propagation characteristics. It works really well. On the other hand, when we go up to millimeter wave, we start to see quite a lot of empty holes there. And especially for the uplink, this is problematic. And this connects to that we have to, you cannot rely on that band only. You need to combine it with a lower gigahertz band in order to make coverage for the user as well. So this really shows that you need to combine, I mean, both the millimeter wave to have the real boost where you have the hotspots, but you also need to have a good deployment for the coverage. And that's yet another challenge when you're going to make, let's say, cost-viable transceiver solutions. Typically in these systems, when you go up to millimeter wave, you can handle 1, maximum 2 impairments in the propagation. Typically, if you have, let's say, reflection or diffraction or something like that, you can handle 1 impairment. If you start to put them on top, so you have to pass a window and then you need to sneak around a corner, etc., then typically you end up in problems, whereas you're not really faced with that for the lower gigahertz. So millimeter wave creates a whole set of challenge from the deployment perspective. Alright, so now we have set the scene here a little bit, and we have realized that antenna array systems are paramount for the deployment and for these radio systems in order to get them to work at all. So that is the next phase of this talk. And if we just look into the different architecture we have at hand, you see that we have 2 categories. We have one in the beam steering domain. This is usually what we call phase arrays, where you line up transceivers in a phase pattern, and you can basically direct energy spatially to a receiving unit. And you will have an antenna gain as a consequence, as a result. This can be done both in the analog domain, can be done digitally, but in the end, it's all about pointing power in the space. On the other hand, the other extreme would be to have digital beamforming, which is more towards massive MIMO. You have a large set of antennas and you rely on pre-coding instead. So your propagation matrix, you optimize that matrix in order to have, let's say, a positive combination of power at the specific user, given the pre-coding, and hopefully noise for everyone else, and so on. We will see a few details about that later. But this relies on basically pre-coding instead. So you're sending layers in the system, pre-coding layers. Now, the trade-off here is quite obvious. In one case, you're sending a data stream, and then you phase align, and then you ship power in the room. In the other case, you need to have a lot of digital streams in parallel, because they all send, let's say, information to each specific antenna port instead. So it's a trade-off between flexibility, what kind of digital processing you have. The data transport is super critical for these systems, because you consume a lot of power when you ship this amount of data. And of course, how many data layers you need to support. So there are trade-offs here. And we will try to see if we can, now when we go between these two, because you realize you can combine these into hybrid solutions as well. And that's what we will talk about in a few slides. But if we start with the beam steering, this is just an overview. Like I mentioned, you point energy in space, and these are the first kind of 5G systems we see today being deployed. They are part of the fixed wireless access offering today, for instance, that we have with Verizon and AT&T, where you, from the cell tower, you basically just point energy towards specific users in time. So these systems rely on that you either time multiplex information between users, or that you use specific subarray systems for different users, but they cannot really use the same frequency time entity. They have to be orthogonalized in that kind of ways. These systems are let's say dependent on that you can orthogonalize the phase steering and your amplitude control in good ways, and that has to do with the side lobes of the systems, because you can achieve pretty good accuracy for the main lobe. I mean, because you have so many elements, the angle accuracy for each element will be smeared out, or let's say you will improve that accuracy by having a lot of elements. So like mentioned in the table here, you have a phase shift revolution of 5 degrees. Now combining 64 elements here, you will have like 1.4 degrees as the beam steering resolution. So that's a clear advantage. The problem is in the side lobes, where you will have a lot of, let's say, shifts and degradations depending on how these systems perform in the amplitude and phase domain. What you do typically is that you try to orthogonalize them, and you use the amplitude, let's say, domain in order to control the side lobes. So you can do tapering, you can do, I mean, just like in a FIR filter, you can try to control the windowing function here. And therefore you can sort of adjust the side lobes. And the figure to the right illustrates, I mean, when you sweep the resolution from 0 to 40 degrees in the phase shift resolution, you see what happens. The main lobe is pretty much unaffected, whereas the side lobes show a huge variation. So therefore it is really important to control this in a good way. The system we are currently developing at Ericsson for the beam steering system looks like this. It's been published 2 years ago at ISCC, and it's a phased array system designed in 130 silicon germanium, and it forms together, when they're put in the box, basically 4 subarray systems, 64 antennas in each, and they're dual polarized. So all in all, you do have some 512 let's say antenna ports that you can support in total. This system is what we currently deploy in the US for the millimeter market, where you have spectrum going from 24 gig to 40 gig. And it is a pure beam steering system where you can set beams in space for specific users. So this is ongoing right now. What's on the horizon, and maybe will take some more time, at least for millimeter wave frequencies, is the digital beamforming. Now this is already in place for low gigahertz systems, where you have a limited set of antenna elements. But in order to scale this up to also fit the millimeter wave space, where you have a vast majority or a large amount of antenna elements, there are some challenges associated. But this is how it looks today. I mean, digital beamforming, typically from a conceptual point of view, what it is that you send in data layers represented by X here, you have a pre-coding matrix Z, and you have your antenna ports, and the pre-coding makes sure that you combine information to the right user. Now there are different algorithms for doing this. You can have maximum ratio transmission, you can have zero forcing, it depends what you would like to achieve. But in the end, it's all about relying on the pre-coding in order to make it favorable for one specific user using all the elements. And it will be, you will create noise in the system, of course, if you have many layers and many users. But this is the basic principle behind it. And it works well in practice as well. We have an example here from academia. This is a test bed at Lund University that they have been running for a few years now. It's a 100 coherent RF element system. And it works at lower gigahertz, 3.7 gig, and they're primarily using it to understand the radio system challenges with these kind of systems. As you realize, this is super bulky. We're talking about 300 kilos, 2.5 kilowatts. You have the software-defined radios there to make maximum flexibility. But this system is the challenge for us now to bring into some commercial product, and that is the challenge. And I think we will hear a lot about this today during this tutorial, because this is on the horizon, but you need to make it cost viable and be able to produce it in a good way, make it having physical properties that can actually fit the deployments, etc. So that's a key challenge. Now, if we try to combine, the best of two worlds in a sense, what would that look like? In the analog domain, we realized that yes, we will have nice antenna gain, we will have low bit rates typically. On the other hand, we will not have the degrees of freedom, and we will not have the capacity that digital beamforming would offer. So, is it possible then to combine analog properties and digital properties here in a good way? And this is what we try to address in the hybrid beamforming scenarios, where you still use a lot of antenna elements. You need to have your gain in place, but you subdivide your big antenna array into subarrays. And these subarrays are treated in, let's say, each subarray can be viewed as an analog entity where you can deploy analog beamforming. But when you combine the different subarrays, you can view it actually as you have different data going to the different subarrays, and therefore you have the digital beamforming approach. So it's a combination of the two different extremes, you might say. The good part here is you might actually get realistic interfaces in place. You will see in the coming slides that you will also be able to trade off when it comes to power consumption, so you can find a good compromise between these two domains. And this is, I would say, currently what is, if you at least look into millimeter wave deployments, this is what will be on the market first, these kind of systems. Then down the road later, maybe we can think of pure digital beamforming systems, but then we need to solve the interface problems. Maybe we need to introduce optics closer to the radios. We need to handle the bit rates more efficiently. But these kind of systems are typically what you will find as the first batch of products coming out. So, if we then zoom in on these antenna arrays and the power consumption and power dissipation. So let's make a short study here, what this is, how this can trade. So what we will use is a quite simple model. It's just intended to provide a holistic view of how different parameters scale. There are so much more details, of course, when it comes to the actual implementation, so we will not go into that. I'm sure some of the other speakers here today will touch upon it in their presentations. But in this talk, we will just zoom in on the, let's say, the holistic view a little bit. And what we have is a subarray. So you should envisage a big subarray that is subdivided into, or a big total array, I should say, that is subdivided into subarrays, indicated here by the color coding. So in this case, we have a let's say a 4x4, so 16 element array, and we divide it into four element arrays. This approach, you can find more details in literature, of course. If you go into the February issue of Microwave Journal, there's a very nice read from both Corvo and Nanoku Wave that also talks about this. And they do it from a more implementation point of view, where they, of course, promote PA solutions and so on. So I would recommend you to read up on that if you find this introduction of mine interesting to study further. So the analysis overview will look like this. We have the data streams coming in. We have a beam steering entity that consists of transceiver circuits. Then we have a front-end aspect where we have the drivers for the antenna elements, dominated by the power amplifiers. We have the array system, the antenna, and then, of course, that corresponds to the spatial separation. And then we have a wanted EIRP at the user. And the EIRP, that's the effective isotropic radiated power. That's usually how we specify the wanted radiated power we get from the system. So that is basically what the PA produce plus the antenna gain. Then you get the EIRP value, and that is what we will use in this study. So, if we look into a few definitions here, we have some parameters we will use. We have, of course, the number of antennas in the total system. We have the subarray size. We have the single gain you get from each antenna element. Typically, if you have a patch that is lambda half and a quadrant, you get 5 dB. That's the inherent antenna gain from a patch. So we will use that one. You have the array efficiency, meaning that all impairments you have in the array as such. We have the fan-out loss that we'll look into, the EIRP value, what each TRX would consume if you only had one branch, not an antenna array, but just one branch. That will also be considered, of course. The efficiency for the PA, and the back-off that we need to use. We also have just the power up or power per batch here, back-off, as a constant or a parameter. And the system is very simple. It's drawn on the right side here. You have the antenna elements, you have the analog element front ends driving the elements, and then you have the beamforming functionality, which is made of the TRX functionality, corresponding to the TRX transceivers. And let's see here. Oh. I'm trying to flip. There we go. If we look into this model, how it's derived, it can be summed up in this equation. So what does it say, really? What is the total power consumption for a system like this? Well, we start with the EIRP value. That's the wanted radiated power we like to achieve in the system. And then we have how these contents will play. We have the back-off, we have the fan-out loss, we have the effective antenna gain, and we have the power, the efficiency of the PA. So the first term here will sum up the power dissipation from the front-end part. It's captured in that term, conceptually. The other part is from the TRX perspective. So that's the transceiver perspective. And as you realize, since we have subarrays, you only need to have one transceiver handling a subarray, because they will have the same information It might be phase shifts, you might be supporting multiple PAs in a beam steering fashion, but from a data point of view, that subarray will only need one transceiver solution. So if we divide the total number of antennas we have in the array by the subarray size, we get the number of subarrays, and there you have the n over m factor. Then the square root of n, that tries to capture the increased power consumption you need to burn in this transceiver system from a dynamic range point of view. If you sum up a few branches of power from the antenna elements, they will sum up in power. That will basically give you the square root in terms of the amplitude, and that corresponds to the additional power consumption you need to drive in the transceiver. So you have the square root of m factor that corresponds to the beam steering properties of the system. So this, so this equation, so this equation as such, I mean, indicates or gives an indicator what the total power consumption will look like. And now you start to see that we can, by looking at these parameters, get a feeling for how they will trade when we increase our arrays, when we sort of adjust the number of subarrays we use, etc. Then you will have an immediate impact on the power consumption of the total system. So, as an example, if we plug in a few variables or numbers for the variables, you see the values here. In this example, we have like the size of 4 in the subarray. The M value is 4, and then we have the patch gain 5 dBi, and we have a number for the efficiencies and the wanted EIRP, and also the just a regular number for the power consumption. Actually, this 190 milliwatt was taken from the Corvo paper, but it makes a whole lot of sense also when you study many of these implementations. So it's just a number, and you look and you see we also have the backup 6 dB of the OFDM, and then we have assumed as this first step no fan-out loss. So here we disregard the fan-out loss. We assume that the antenna array is, you don't have any power dissipation due to that at this stage of the analysis. And if you just plot this as a function of the total number of patches in the array, you see that the total power consumption will have this banana shape with a clear optimum, actually. So the left-hand side is dominated by the PA side, the side related to the EIRP, the radiation part of the equation. And of course it has a declining slope since you have the n factor in the denominator. That's part of the antenna gain. So you see that the slope here will start to, the power consumption will go down when you start to increase the antenna array size. On the other hand, what happens is that when you increase the antenna array size and you keep the subarray size the same, you're basically just adding subarrays. That means that you're adding transceivers in this system. And that is why suddenly the other term is starting to increase when you go up in array size. So the beam steering term, or part of this total power consumption, is then going in the other way around, going in the opposite, and therefore you get this local minima, an optimum. And that is happening when these two terms are equal in size. So if we can nail down the equations, and you can find values for the n-opt and the p-opt. I mean, for a given EIRP and a given antenna subarray size, in this case m equal to 4, you can simply calculate, okay, given this simple model, what would be the most efficient setup from an antenna array point of view. And what we now can do is we can start to play around with the M factor. So in this graph we see, okay, so now we had, before we had we had an NEM, let's say, in subarray size equal to 4, and we swept just the array size. If we now look at when we have different subarray sizes, going from 1 here, that means that each element is just a subarray, so a full massive MIMO system, all the way up to 64, meaning you have huge subarrays, so you rely on, to a large extent, analog beamforming. You can see that these curves, they will sort of be on top of each other. What's happening is that the left-hand side remains the same. That is, since we have still not introduced losses in the antenna array, it's only related to the total size, the N value, and the EIRP, and then the imperfection of the that's mentioned with the efficiencies and backoff and so on. So they will all be the same on the left-hand side, whereas on the right-hand side, when you scale up the antenna arrays, we realize that if you have larger subarrays, then you will have a smaller impact on the upscale of transceivers needed to feed the subarrays. Therefore, it's advantageous here to have large subarrays. So the bigger subarrays, the better it is in this regard. And we can see that, of course, the gain it slows down a little bit. I mean, when you go up here to 64 elements in the subarray, you have a very flat optimum. If you would decrease further, the curves would pretty much, be on top of each other. So this is just illustrating, the different trade-offs here. But what can be noted in this model is that we have a square root dependency of the EIRP for the optimum value. So if we have an EIRP of 52 dBm on the left-hand side, and let's assume that we pick an optimum here for, it's the green curve, so it's 16. We have 16 patches in the subarray. You see that in order to scale up to 65 dBm EIRP, we need to add more subarrays in parallel, and then the power consumption we will burn will be proportional to the square root of the power difference of the EIRP. So in this case, we scale up 20 times, we consume 9 watts to the left, we will consume 40 watts to the right. So you have this square root dependency if you just keep the subarray size the same. What's more interesting now is to look into when we introduce the fan-out losses, because this will bring the system to a new dimension. If we assume that when you have split the signal in the subarrays, even though they're coming from the same digital source, you have the same transceiver feeding the antenna arrays, or the antenna patches, sorry. But since one transceiver will feed multiple patches, you will have a split fan-out loss in the system. And then you realize that the larger subarrays you have, the more you need to split the signal, the larger the loss will be. And when you introduce this parameter in the antenna array, you start to see that there is no longer, you cannot longer say that the larger subarray is better from a power perspective. You start to see that there is actually an optimum when it comes to the subarray size in regard to the total array size. So the fan-out loss is just modeled as let's say a loss per split, and then you have the log 2 times m. M here is as you know, the size of the subarray. So every time you double the subarray, you need to split yet a factor of 2 here, and therefore you have this component log 2m. And what's seen in the picture is that what's happening is that the larger subarray, in this case the 64 element subarray, is shifted to the right. So they also previously we saw that on the left hand side they were all on top of each other more or less, because you didn't have any M dependency in that term, because the LA was not part of we didn't consider that term in the equation. Now we consider LA, meaning the loss, the split loss, and that has an M dependency, meaning that when you go to very few elements where you have this dominating effect of the PA part of the equation, this LA factor will have a big impact for the larger subarrays, since you have to do a lot of splitting. Therefore, the whole curve is shifted to the right, and for each subarray size, or each array size, I should say, you see that there is an optimum subarray size. And you can calculate this, and you have the equations here. But if we look in the graph instead and see what's happening, we see that when we scale up the array size, the subarray size, the optimum subarray size will also increase. But there will not be a given ratio. It's not like you could say that, okay, there should be a specific constant if you divide the total array size with the subarray size. There will be a nonlinearity here. And that's illustrated by the curves on the right-hand side. It's also quite visible that when you increase the loss factor in the subarray, of course the subarray size will have to be smaller in order to have an optimal system, because the more you split the signal, the more you lose. And if you have large subarrays, you will split a lot. Therefore, that will be penalized. So that illustrates just the difference between the curves. So if we look into the number of subarrays in the system, it looks like this. It's basically the same curve as before, but now we have just take the inverse, you might say. So we look at the number of subarrays. And then we can see that when we have small arrays, then when the array size is small, we're going towards a massive MIMO system. You see that the optimum M value is going towards 1. We will have basically as very few splits in the analog domain. That's more favorable. So if we go all the way down to, let's say, a very small array size given the EIRP, then it will end up in the digital beamforming as being the most power efficient solution. Whereas if you go for very large arrays and you will have to which you will need in order to have good enough EIRP, I guess, and then you see that it's not really that obvious. Then you will have the trade-offs, and eventually for as you can see on the left-hand side, for a subarray with an EIRP of just 52, it's actually most advantageous to have just the pure analog subarray. For the whole system, you have M equal N. That means you have just one digital stream, and then you have all the splitting in the analog domain. You have a basically phase array system. So you go between these two extremes, and as you can see, it connects to the split you're having in the antenna, the EIRP you're trying to achieve, and you have these trade-offs. Now, like I mentioned in the beginning, what we have done so far is just looking into the penalty for going for analog combining. If you have beamforming in the analog domain, we have the square root of M factor in front of the beamforming term. Now, one can also envisage to have that beamforming in the digital domain. There's nothing preventing us from doing this. It's basically just where we put the data converters. And if we do that in the digital domain, we see that there will be some shifts in the equation. The left-hand side corresponding to the PAs and the EIRP value we try to radiate is untouched, is the same. Whereas what we have done is actually now moved the data converters, and I mean, I say it's untouched, but you realize we have moved the data converters to that side of the equation, and you might consider, well, wouldn't have an implication. Well, in practice, we know that the PA is dominating the power. In practice, we also know that we have a split between downlink and uplink. Typically, 5G systems will have an 80-20% split. So you have 80% downlink, 20% uplink. So the PS will clearly be dominating. So moving the mixed signal circuits into that side of the equation will not make too much of a difference from this holistic point of view. I think we can do that without too much drama. So what's left on the beamforming side is now a pure digital entity, which is called DFE here, the digital front end. And if we do the beamforming in the digital domain, we exchange the transceiver power with some kind of digital front-end power. We still have the N over M factor, because we still have the relationship between how many of these we need, I mean how many subarrays in comparison to the total array size. But then the square root of M factor present in the analog domain we cannot use anymore. We have to use a new scaling factor. In this case I call it K. So we will look into that scaling factor now. And the system is depicted on the right hand side, and you see it resembles a whole lot of the previous model we used, but just some smaller implications. If we now look into the scaling factor, you could say that the dynamic range corresponding to the effective number of bits, the ENOB, for one branch here, we call that ENOB and then M equal 1. That's how it looks. For each antenna element, each branch, this is the ENOB you need to handle in the system. And now you start combining multiple branches in the beamforming entity. So what happens then? Well, you have the ENOB still, but you need to add the effect of that you now add power in the digital domain. And in essence, it means that for each, when you double the dynamic range here in the amplitude, you need to add 1 bit. So for each, if you have 4 additions here, as illustrated in the example, you will end up by needing to add 1 bit compared to the single branch dynamic range. So the equation will be the ENOB times for one branch plus the log 2 square root of m. That is the equation from this model point of view. This is just quite, I mean, it is a model after all on a quite high level. So of course there could be other effects being present, but I think this captures the phenomena to a large extent. And if we assume that we have a multiple accumulate kind of structure in the digital front end, we can derive a K factor that is proportional to the ENOB we need for one branch plus the log 2 square root of m divided by the ENOB for one branch, and that will be our K, the scaling factor of this power consumption. And what we assume is then that we linearly more or less add the MAC operations as we scale up the digital. And you realize that that may not be true necessarily in a real system. You can imagine that if you have a DSP functionality, if you have a larger set of digital operations being present, the scaling factor could potentially be flat almost. But in this system, just to showcase the difference between digital and analog, I decided to use this scaling factor, which would be sort of true if you have a pure multiple accumulate sort of system. What's interesting to notice here, if we now compare the square root of m as we had in the analog domain to the K factor that we have in the digital domain, and see what will happen for large arrays. As you see that it's very advantageous to go digitally for large arrays, because this fan-out, or when you combine multiple streams into your transceiver, just doubling dynamic range, I mean, you add a bit basically in the digital domain, whereas in the analog it grows much faster. So what's illustrated by the curves here is that especially when you have a significant dynamic range, so you have let's say quite many bits in the digital to handle the E knob for one branch, then the scaling will be very advantageous. If we plot the comparison, if we have a few parameters here and we compare the analog system and the digital system, when we combine the branches, we can see these two plots. And as you see, the left-hand side is pretty much untouched. That relates to the EIRP. That's the same for both systems in this model, so it remains the same. Whereas the right-hand side shows quite some difference. If you have a small subarray system, so you have, in this case, the extreme, just subarray equal to 1, meaning that you have one patch per transceiver. I mean, you have full MIMO, you have massive MIMO, you have a full digital beamforming. You see that suddenly the power goes up really quickly when you scale up the antenna array. And the reason is that the digital front end, we can assume that it consumes more power than the analog transceiver. The starting point is that it consumes more power. I've estimated that it consumes maybe twice the power. That can be debated, of course, but if you look into real systems today, this is not too far away from the reality. So if we have a factor of 2 there, you see that it becomes a very, let's say, disadvantageous when you have a lot of these digital front ends, meaning that you don't do any combination at all. You have this massive MIMO system. You have the subarray size equal to 1. Then they become very inefficient. But as soon as you scale up the subarray size, the digital system becomes much more advantageous. So if you compare the 64 subarray size case, you see that the digital shows a much maybe is a strong word, but it shows a lower power consumption than analog. And it drops quickly, I mean, as soon as you scale up the subarray size here. So this is just an illustration of the difference between these two tactics or approaches one can use. So then a few reflections here on my side is that, first of all, we saw in the presentation that we have two different parts of the equation that we need to balance. That is the EIRP related part that corresponds to the power radiation of the system that we need to produce. And then we have the beamforming part that consists of the transceivers we will use in order to produce data streams to the subarrays. And when they equal in power, we get some kind of optimum. So that's an important observation. We can also see that if you noticed, I mean, the size here of the arrays, we see that usually this optimum is in the range of a few hundred elements. Now, that's given this model, of course. If we were to deploy this in reality, there are other constraints we need to look into as well. Where do you have your users? Would you use the same, and let's say, would you have the same degrees in the vertical domain as the azimuth domain? Those kind of aspects will add on top here. What kind of sectorization will you use, etc. So these antenna arrays will not necessarily be a very simple model like this, a square model or so, but have a different shape, and also dictate a bit how many subarrays and streams you will have in parallel. Another factor we need to consider is the uplink, which is usually limiting these systems. We have a much lower power capability in the uplink than in the downlink, meaning that the link budget to a large extent is determined by the uplink scenario. That means that the uplink will determine the base station antenna size to a large extent today, and meaning that the base station in many cases is over-dimensioned for many of the users. And that also will play into, okay, what kind of, how you will steer that antenna array, how you will set it up. The good part is if you have a very digital system, that can be handled dynamically. You can go between having analog steering properties to having more a massive MIMO approach. So going from analog to digital will provide you more degrees of freedom in these systems, and they can be dynamically configured. And finally, as we saw, the digital domain beam steering is efficient when you scale up the power, the ERP, and the number of, and the subarrays, the subarray size, that is. So that's also a conclusion. So in summary then, 5G is happening now. I think that's obvious to everyone in the room. We have the fixed wireless access systems, purely reliable on, or they rely on phase steering. They're already out today. They're shipping. The AS systems, they are needed for coverage and capacity, especially for millimeter wave deployments. We will need band aggregation, as we saw in one slide. I mean, coverage will be a big limiting factor here, so we need to combine multiple bands. That would complicate the picture further, I mean, when it comes to the realization of these systems. We have trade-offs between coverage, throughput, and cost, so that will lead or move us towards hybrid systems, at least in the beginning, until we have managed to get digital beamforming in place. In a good way, in a cost-efficient way, also for millimeter wave. And the model I presented is a simple, holistic model just to provide some first glimpse into a different parameter scale and how it will affect the total power consumption in these array systems. I was asked to provide or give some highlights to a few papers in this year's conference, and I found at least 2 papers that correspond very much to the arrays I've been talking about. So please have a look at those. Go to the sessions if you have the availability to do so. And then, as a final remark here, or my acknowledgements, of course this material I presented has been compiled by various inputs, so I'm thankful for all that, and especially to Sven and Lars, working in my team at Ericsson, for all the discussions we've had over the years about these different concepts. And then there's a set of references for you that you can use for further reading if you have the interest. Thank you.